React might look simple on the surface. You change some state and the UI updates. But under the hood, a lot more happens than most developers ever see. Today, we're going to walk through the entire journey of a React render, from the moment your state changes to the exact moment the browser paints pixels on the screen. Everything in React starts with a state change. Whenever state or props change, React schedules a re-render. But React does not update the DOM immediately. Instead, React creates something called a work request. You can think of it like raising a tiny update ticket in React's internal task manager. This is important because React might delay this work, merge it with another update, or even drop it entirely if it's no longer needed. But how does React decide when to run this update? React uses a scheduling system called Fiber. Fiber is React's internal engine. It's a tree structure that mirrors your component tree, where every component instance becomes a fiber node. Each fiber contains the component type, its props and state, reference to its children, and importantly, the work it needs to do. You can think of each fiber like a small JavaScript object with a to-do list. When an update happens, React doesn't re-render everything. It walks the fiber tree and decides which fibers actually need work. This process is called reconciliation, and we'll talk about that in a moment. React uses lanes to prioritize your update. Not every update is equally important. A click on a button is urgent. A network request finishing is less urgent. A background update like a transition is even less urgent. React categorizes updates into something called lanes, which give each update a priority level. High priority lanes run immediately. Low priority lanes wait until the browser has free time. This is a huge reason why React apps feel smooth even with a complex UI. Now let's talk about the render phase. Once React decides it has time to work, it enters the render phase. In this phase, React does not touch the DOM. Instead, it builds a new virtual tree representing what the UI should look like after the update. Here how it works. React starts at the root fiber. It calls your component function. It reads your new props and state. It builds new virtual elements. Then it moves on to the next child, and the next one, and so on. React continues down the fiber tree trying to figure out what the new UI should be. But here's where it gets smarter. React compares the new virtual tree with the previous committed tree. This comparison is called diffing or reconciliation. React checks, did the component type change? Did the props change? Did the children change? Can this subtree be reused? If nothing has changed, React bails out. This means React skips the entire subtree, a huge performance boost. If something did change, React marks this fiber with a flag that tells the next phase what needs to be updated. React doesn't only create virtual elements, it creates a list of precise mutations it needs to make. Let's talk about effects. During reconciliation, React also figures out which effects need to run. This includes use effect cleanup, new use effect calls, use layout effect, side effect subscriptions, refs, and more. React does not run effects now. It just records what needs to happen later. Once the virtual tree is ready and all changes are known, React moves on to the commit phase. This is the phase where React updates the actual DOM. React performs changes in three steps. First, before mutation, React runs cleanup functions for layout effects. It prepares the DOM for incoming changes. Second, mutation. React applies DOM updates, inserting nodes, removing nodes, updating attributes, changing text. This is the only part of React that blocks the main thread. Third, layout effects. After DOM updates, React runs useLayoutEffect, then browser layout and paint, and finally useEffect. This phase is always synchronous. Once React starts committing, it finishes without interruption. This is why React tries very hard to minimize how much work reaches this phase. React makes smart optimizations along the way. To keep apps fast, React uses several techniques. Bailouts. If probes are the same, React skips entire components. Memoization. Using React.memo or useMemo and callback helps React reuse previous values. Skipping updates with keys. Keys help React understand which elements moved, allowing more efficient reordering. Concurrent rendering. React can pause work, resume it later, or abandon updates entirely if a more urgent one appears. These optimizations are why React apps remain smooth even when the UI is complex. Once React finishes the commit phase, the browser handles layout, compositing, and painting. And your UI updates on the screen. And remember, all of this happens in a fraction of a second. So when someone says React re-renders, it's not just calling your component again. It's scheduling tasks, evaluating priorities, building a virtual UI, diffing fibers, collecting mutations, optimizing work, updating only what's necessary, and finally committing precise changes to the DOM. That's the real engine behind React's speed and reliability. And now you understand it better than 99% of developers.